Well, hello and welcome again to our journey into Algebra and Number Theory, and we've been looking in this section, we're looking at quadratic reciprocity. So we've defined a quadratic residue to be a square modulo m, and we're restricting our m's to be primes, and a quadratic non-residue is a non-square. We saw some examples last time, and also how to calculate the residues, the squares and the non-squares, by using primitive roots. That's a very slow and tedious way of doing things, and we want to be able to deal with much larger numbers, and we want to find some way of telling whether a given number is a square, that is a quadratic residue or not, modulo a prime p. And we want to be able to do it for large numbers. So for example, is 3127 the square in Z 12713? Well, it's not. You certainly can't do it by writing down all the squares here, because that's very slow. So Euler, always a great name in number theory, gave the following test for this. He didn't express it quite this way. He didn't use mod arithmetic, but he certainly understood what was going on here. So here's our test. If p is an odd prime and p doesn't divide a, then x squared is congruent to a mod p has a solution. That means a is a square modulo p, if when you raise a to the p minus 1 over 2 you get 1 modulo p. Moreover, if the answer is minus 1, then the equation is not soluble. So if a to the p minus 1 over 2 is minus 1 mod p, then a is not a square modulo p. And the proof of this, once we've got primitive roots, the proof of this is very easy. So we saw that in the preceding theorem, that if g is a primitive root modulo p and a is a quadratic residue, then a has to be an even power of g mod p for some integer k. And hence, if we simply raise a to the p minus 1 over 2, that gives me g to the 2k to the p minus 1 over 2, which is g to the p minus 1 to the k. G is a primitive root, and so we know g to the p minus 1 is 1, and that's 1 modulo p. If a is not a square, it's not a quadratic residue, we saw before that a then had to be an odd power of the primitive root for some integer k. And again, simple calculation completes the proof. If we raise this to the power p minus 1 over 2, we will end up with arriving at minus 1. You do the calculations on that. So a little example of how to check this quickly. So is 3 a quadratic residue modulo 23? So we take 23 minus 1 over 2 is 11. We calculate 3 to the 11 modulo 23, and after some arithmetic we get 1, and that tells me that 3 is a square modulo 23. Doesn't tell us what it's the square of, it just says that it is a square. So note that Euler's criteria is not all that easy to apply for large numbers, because for large primes here, this power is going to be big, and this is going to take quite a bit of computation. So we're going to still need some more machinery to be able to deal with large numbers, but Euler's criterion is not a bad start. The next concept is that of the Legendre symbol, which is just a nice example in mathematics where you introduce a symbol that does a lot of hard work for you and actually makes life easier. So in order to develop a more practical method for dealing with quadratic residues, we introduce this thing called the Legendre symbol, which looks like this. It's brackets a over p. It looks a little bit like a fraction, but you should not think of it as such. And so this symbol, Legendre symbol a over p, so p is our fixed odd prime, and a is the number that we're looking to see whether it's a square or not. We're going to define this to be 1 if a is a quadratic residue mod p, and minus 1 if it's a quadratic non-residue mod p. Now if you've have a look at all of my other YouTube videos on analytic number theory, you will have seen that this really is just an example of a much more general thing called a character. This is a very simple character here. It takes the value 1 if a is a square, minus 1 if a is not a square. Where a and p are 1 and p is a prime. Well, we generally take p to be an odd prime. 2 is always a pest. Now we can restate Euler's theorem as follows. This Legendre symbol, we can now say, well, it's 1 or minus 1, depending on whether a is a square or not. And we know from Euler's theorem that depends on whether a to the p minus 1 over 2 mod p is 1 or minus 1. So this gives me a nice little connection between the Legendre symbol and this quantity here we get from Euler. So just as an example, I want to find 3 over 5. So the Legendre symbol 3 over 5, it's asking us, is 3 a square modulo 5? So to do so, we simply take 5 minus 1 over 2, and we work out 3 squared, which is minus 1, and that means the Legendre symbol is minus 1, and that tells us 3 is not a quadratic residue modulo 5. Now just note, of course, trivially, that 1 over p and a squared over p are always 1 if a and p are relatively prime. Now once we've got a new symbol, we'd like to see what are the rules of the game for that symbol, and so the Legendre symbol has a number of lovely, very simple properties which we can use to evaluate it fairly quickly. So we're going to assume that a and b are relatively prime to p. P is an odd prime. Then, if a and b are congruent modulo p, then their Legendre symbols are the same. So if a and b are the same mod p, then a is a square mod p if and only if b is a square mod p, is another way of saying this. Obviously a squared, that's trivial. A squared over p is 1 because a squared is obviously a square. Now a very useful one is this one that says if you've got a product of two numbers here, a times b, then these don't even have to be relatively prime to each other. Then you can split this into a over p and b over p. And this is, I leave this as an exercise. This is really easy to show. You simply go back to the definitions. So, some examples of how useful this particular technique is. If I'm looking at 47 over 17, so I want to know whether 47 is a square modulo 17, well, I notice that 3 times 17 is 51, and so I can replace the 47 by 47 minus 51, which is minus 4. Now minus 4 is minus 1 times 2 squared, and 2 squared on 17 is 1, so I just get minus 1 on 17. And now I can use Euler, or I can use the fact that 17 is a 1 mod 4 prime, therefore minus 1 is a square, so the answer is 1. Or I can use Euler and say this minus 1 to the 8, which of course is 1. If we look at the Legendre symbol 19 on 5, again I can read 19 modulo 5 and write it as 4, and 4 is obviously a square, so that's equal to 1. Minus 9 on 13, I can split this as minus 1 on 13 times 9 on 13. 9 is a square, so this is the same as minus 1 on 13. And then again I can say that 13 is a 1 mod 4 prime, so the answer is 1, or I can use Euler and take 13 minus 1 over 2 is 6. And I leave you to have a go at this one to show 5 on 17 is minus 1. That takes a little bit more work to do. But I'll give you a hint here that 17 times 2 is 34, so that might help you a little bit with this, but there are other ways of doing it. Now, if the numbers are large, well, the computations can still be very long and tedious. So we still want to press on. We want an efficient way, a very quick way of trying to evaluate these Legendre symbols. So I simply note here earlier that our theorem 2 can now be stated in this way, that if p is an odd prime, then minus 1 is a square mod p if and only if p is 1 mod 4. That is, the Legendre symbol minus 1 over p is 1 if and only if p is 1 mod 4. And the proof of that is very simple. You just apply it. You can give a little proof of this using Euler's formula. So this is the same as that by Euler. And this will be 1 if and only if p minus 1 over 2 is even, i.e. if and only if p is 1 mod 4. Now, as another little corollary here, if you take the sum of, because exactly half the numbers n are squares and half the values of n are non-squares in ZP, if I take the sum of the Legendre symbols, I'm going to get 0, because half of these will be plus 1 and half of these numbers will be minus 1. Well, in order to get to our main result, which is the quadratic reciprocity theorem, we're going to need to develop what is called Gauss's lemma. Gauss's lemma is a stepping stone to a much more powerful result we're going to get to, called the law of quadratic reciprocity. Gauss's law, however, as well as being a stepping stone to the quadratic reciprocity theorem, it's also, as we'll see, particularly useful for dealing with the case when a is 2. And we'll have a look at that see what Gauss's lemma says, and we'll go through the proof of that in the next video.